So we're going to be looking at a sample question. We're going to run through some information regarding organic compounds. Again, I am Mr. Thomas. Welcome to Buckle Down Tutoring Services. The question would have given us four organic compounds. And when you look at those compounds, what formula is being shown for these compounds? What formula is being shown for A, B, C, and D? Anyone?
The structural formula.
All right, the structural formula, great. And so we said the structural formula is like a two diagrammatic drawing. So in 2D, and you basically present with the bonding, covalent bonding of the various atoms that are in the compound. So if we look at A would have looked like this. Now, when we get an organic compound, um, you need to know the functional group of the different organic compounds, and it will make it very easy for you to identify to which homologous series the organic compound belong. Now, each organic compound have a functional group. So anybody can tell me what's the functional group of an alkane? Alkanes. What's their functional group? So the functional group would have been the carbon to carbon single bond. So in an alkane, and that's why when you really examine an alkane, the reaction can take any place where you have that carbon to carbon single bond. So this is for an alkane. Just and like I said, I'm just doing a quick overview of organic chemistry utilizing this question. What do we know about alkanes? Alkanes are considered to be saturated, meaning they're not able to have any other form of hydrogen or any other form of atom being added without something being removed. When the meteorologist says that the cloud is saturated, and so you have precipitation or you have rainfall, the same concept. The water vapor in the sky, what that is what condenses and forms the cloud. So if it can't hold anymore, then it's just going to fall as rain. Now, when you think of the carbon to carbon bond, we know this is the bond of a covalent situation where the carbons are sharing. So when you examine this bond, both these carbon atoms are actually sharing electron. Now, one thing we want to remember, once you have carbon, carbon has four valence electron, and so it is capable of forming various lengths of carbon to carbon compound. And that's why we have so much variety of organic compounds out there, because of to the extent at which you can have different bonding, different structures being formed. No, carbon will always, and that's the key that you need to remember, because it has four electrons, it will always have four of these strokes if you want to put it that way. Yeah? And especially if we're dealing with the double bond, you need to be conscious that that carbon already have a certain number of strokes. So a popular mistake, especially with the alkenes. So we need to remember that. So going back, alkanes are considered to be saturated. They have the general formula CnH2n plus 2. And what this means is that for every alkane, if you have an alkane, you can add this to the name, or add it to the molecular formula and see if it applies. If it applies, then you can consider it a alkane. Now we know about the prefix, and so organic compounds comes with a prefix and it comes with a suffix. So the ending for any organic compound that's an alkane would have been ane. So you have propane, methane, butane. So once you know the ending, or you see a name and it ends with this, you know you are now in the realm of the alkanes. And then the prefix tells you the number of carbons that are present in that particular organic compound. So if you see prop, and one thing I want you to do as a student, it might be simple, but you need to know the prefix and the number that they represent. So the number of carbon is, usually I don't see CXC going beyond 8 or sometimes even 6. So I normally provide from 1 to 10. So we have meth, eth, prop, but, pent, hex, hept, oct, non, and dec, in that order going straight to 10. So what you want to do is to be familiar with those prefix so that you can match the name. Now, again, it's just a quick overview. We want to have persons being familiar with. Now, organic compounds, we have also the alkenes. And the alkenes, they have the carbon to carbon double bond as their functional group. And so once you're seeing this, it simply means you're now in the realm of the alkenes, the homologous series of the alkenes. Now, alkenes are considered to be unsaturated, and this is because this double bond between the carbon has a possibility of breaking and accepting other atoms, hydrogen or halogens or nitrogen or any other um, atom that is possible of forming organic compounds. We have a few that can accept metals and all of that. So we are now looking at the general formula. So the general formula for an alkene would have been CnH2n. And for ease, I tell students, technically, when you look at this, any amount of carbon you have, you technically have twice the amount of hydrogen for an alkene. So automatically, the alkene should be easily jumping out at you when you see the molecular formula. We did say that this that I'm displaying here, and I soon get a little bit into it, is the structural formula. And it shows the drawing, how they are attached with the covalent bonding of each atom within that particular compound. Now, again, sometimes we are asked to do specific things. So they will ask you for the structural formula. They can ask you for the molecular formula. They can ask you for the empirical formula. They can ask you for a condensed structural formula. You should be able to move between these different tasks as a chemistry student going into the exam. So you should be able to move and look at the structure and know the name. You should know the name and should be able to draw the structure. You can see the name and know the molecular formula. You can look at the molecular formula, draw the structure, the molecular formula, know the name. You should be able to move back and forth. So here we have a compound, and we said that when we look at the paper, they call this A. Now, again, this is the structural formula. If we want to talk about a condensed structural formula, what we do is to zero in on each of the carbons. And see here, I left out one of my hydrogens. One of the carbons, this carbon in particular, has on 3 hydrogen. The next one has on 2 hydrogen. The next one has 1. We want to represent that double bond. And sometimes, to be specific, persons would have drawn the H behind the carbon to show that it is really the carbon to carbon that has the double bond. So if you want to show the fact that the double bond is really between the 2 carbons, we can represent it like this. So this is what we call the condensed structural formula. Yeah, we said that we also have a molecular formula, and we know this is an alkene because we see the functional group. Once you know the functional group, it also helps you in determining, the concept of the name, the structural formula, all that info. So if we were asked to write the molecular formula again, we can go to the general formula to help us. So the general formula is CnH2n. So automatically we see where we have 4 carbons. So the molecular formula is C4. And as I said before, once you're in the realm, the hydrogen will be 2 times the carbon. So if it is 4, automatically we know that the hydrogen is 8. So this is what we call the molecular formula. So it doesn't show how the atoms are connected or being shared or bonded. What they do is to have a total number of each atom within the organic compound. So we know that we don't know how they are positioned. If you notice, you're not seeing the fact that you have a double bond in the molecular formula. So what is really important is for you to know the general formula, to apply it to the molecular formula, and once it works, then you're going to have a situation you would know that it is that particular homologous series. And let me just show you. If I use the general formula for an alkane, it wouldn't work here because the general formula says if I have 4 carbons, the amount of hydrogen would have been 2 times the 4, which is 8, plus 2, which gives us 10. And this molecular formula is C4H8, not C4H10. And so again, knowing the general formulas for the organic compounds put you at an advantage because not all the time you'll see the structure. So if I see the structure, I automatically can say, okay, I'm seeing the functional group, and so I know that it is an alkene. But what if you got the molecular formula? You're not seeing any double bond. All you're seeing is the total number of hydrogens and carbon that are in this compound. And so you can apply the general formula, and then you deduce that it would have been an alkene. So I want you to get familiar with that going into the exam. The next thing we said that sometimes we are asked about the empirical formula. And the empirical formula, technically, it just gives you the lowest ratio of the atoms that are within that organic compound. Can this be broken down into a lower term?
Yes, sir.
And so if it's broken down, what do we get?
CH2.
And so the empirical formula right there would have been CH2. Now we want to venture into the naming of this compound. Now, in providing the name of any organic compound, technically you look at the longest chain. So the longest chain has 4 carbons. And so I'm mentioning this because sometimes we forget that we do have branches within organic compounds, and how you name those, again, the backbone would have been the longest chain. Now, the functional group, they are so important. They get preference. Now, especially for the alcohols, especially for the alkenes. Usually, and if you look at the question, if you look at D, and I'm just saying D is an acid, an alkanoic acid. Usually you may even see in some books the past name where they refer to them as carboxylic acids, or you will see them say organic acids. Now the organic acids, when we write them, or draw the structures, the functional group is always at the end, right? And so you don't have a problem in terms of naming those. They don't really give a little issue along that line. They won't give you, if you're a student, and we should speak about that as well, they won't give you acids to talk about isomers, because the functional group always appears at the end. So you won't get that is either the alkane, the alkene, or an alcohol. You get to show your knowledge about isomers. So what is the name of this? We said that we look on the concept. We look on the concept of numbering our carbon. What is the principle behind numbering your carbons? You number them in such a way that the numbering order that you're going to be taking. And so because there's no real um, direction between these compounds, there's not, we know typically as a human being, we read from left to right. But when you're dealing with the organic chemistry, you can go from right down, sideways, left and back and forth, and all of those. But the key that you need to remember is that while you do that, you should ensure that the organic compound, its functional group, is located on the carbon that has the lowest number possible, right? And so when I look at this, if I number from this way, 1, 2, 3, 4, then the functional group starts on carbon number 1. If I number from left to right, like how we normally read, 1, 2, 3, 4, then the functional group starts on carbon number 3. And so if we jump and say, okay, yes, the name of it should influence by saying the 3, then we're going to be in problems, because the name of it should be influenced by the 1, because that's where the first carbon, is where you're going to have the double bond being drawn. And so this is very specific, guys. Why? Because sometimes they ask you in showing reactions, they ask you in writing name, in writing the structural, drawing the structural formula for a specific. And so for this, we said we would have started, so we know that whatever name, it's on the first carbon. So we look at the amount of carbons in the longest chain, we're seeing 4. And so we know the prefix for 4 is but. It is an alkene, we established that. And so it should end with "ene." Now, the thing about it, if I just say butene, the double bond can be in various locations. Well, it can be in 2 locations, technically. And I'm going to show you even why just now. It can be in 2 locations. And so you have to tell persons where to put the double bond. So you can't just leave it at butene. If some questions may not be as specific, but if the question is specific, then you have to know how to address that. So we're going to be putting 1. And this one is now indicating to persons, you see the name 1. Automatically, the name talks about, or the number rather, speaks about the carbon in question. So this is telling us that the functional group, and it also applies for branches. So if you see a branch, whether a bromine or a halogen, or a methyl or a ethyl or a propyl group, those numbers tell you which carbon it is on. So when I write a number, if I have a letter following, I use a dash. If I have 2 numbers, I use a comma between them. This is very critical when you're dealing with organic chemistry. It's just a principle. Students, oh sir, may I have to do that? Or you leave it off. Sometimes you may end up losing marks for those things. Drawing the proper structure. So sometimes students leave out the bonds that are showing. So persons are drawing carbon with hydrogen bonds, and that we're just seeing this. You're not putting in the fact that they're bonding. So that too is an issue that you need to, clear up. Don't practice to do that. So this is 1-butene. And we say 1-butene because the double bond gets the lowest number. We wouldn't say 3-butene, because how we would be forced to number the carbon is in such a way that the double bond, the functional group, gets the lowest number possible. Now, alternatively, you basically sometimes see where in textbooks or even online, the number appears in between. So they have the prefix, which is for the amount of carbon, then you have the number. So we have what we call 1-butene, or but-1-ene, sorry. And so you should be able to see a name and draw the structure. You should be able to see the name and know the molecular formula. You should be able to see these things and move back and forth. Once you can do that, you would have put yourself at an edge in terms of organic chemistry. Now, just to highlight, if I had drawn it like this, and just forgive me if I, due to the interest of teaching, I may not necessarily put in all my hydrogens, but please just remember that hydrogens are there. Let's say you should lead by example, so let me put them in. Now, is this compound different from the one that we just looked at? If we go through the same process of providing numbers for the carbons, you can say this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, or this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. We find ourselves in a situation where we're asking the question again, is it that we number from this way where we start at carbon number 1, or is it that we number from this way where we end up starting at carbon number 3? And so the rule is we always ensure the functional group, and in this case, the double bond, or even if it's a branch, the double bond, the branch, they get preference. If, and you can write this down, if you end up with a branch, if you end up with a branch on a like an alkene, the double bond gets preference over the branch. So if you have a branch somewhere here, we have a methyl group, the double bond will get the preference. So you still number in such a way to favor that the double bond is on the lowest carbon, because the double bond, the functional group, is very important. That's where the action of reactions will take place. So it is the highlight, it is in the spotlight. So even if we do the situation where we put the double bond down here, we recognize that, hey, this still creates a situation where I have one butene or but one in. So technically, these two are just mirror images of each other. So there's no difference within that type of compound. Cool?
Yes,
Cool.
sir.
I know I've been talking, and so let me just get some feedback. Where or what type of homologous series it is. So when we look at this again, what do we call this? This is a what type of formula? Type of formula is this?
Your formula.
I'm not sure if it's only for me, but you broke up. I didn't hear clearly.
Sir, the structural formula.
Wonderful. And so the structural formula, it shows the bonding that is happening. And again, each time we see that this carbon has those 4 strokes because carbon has 4 electrons on its outer shell that can be shared. Now, what's the molecular formula for this? Now, there are 2 ways that sometimes we represent the molecular formula. So, one way is to treat the OH group separate. So, we have C, we say we have 3 H's. As I said, we're going to be treating the molecular formula different. Yeah?
Yes, sir.
Or we can put the hydrogen within. So you have to be careful. If you see this, this is still representing this compound. So all it did was to now couple. But you have to be mindful that you see again the general formula is CN H2N plus 1 and we have the OH. So the general formula, we don't take into consideration this H in the functional group. Excuse me one second. Cool. So if we're going by the general formula, we're basically going by this. This is what we use. Because when you say N is 1, 2 times 1, 2, plus 1, 3. So that's how we get that. And then we said that we have the functional group right there. Yeah? But we can also represent it like that. So what is it that we call this compound? What is it that we call this compound?
Sir, like the name of it?
Yeah, the name of it. What would be the name of this?
Methanol.
So methanol.
Right.
So again, as we said, we end with anol. We use the prefix. Only one carbon is there. So the prefix for one is meth. So we get methanol. Cool?
Yes, sir.
No, because it's only one carbon again, I mean, we don't have to say one methanol. We don't have to say one methanol. Why? Because one carbon, automatically the functional group must depend the one carbon. Now, if we had a situation where we had more carbons, would we call this, a matter of fact, would we, I'm just gonna jump and tell you the name, we just did butene, right? And we spoke about, giving preference to the double bond. So would we call this 3-butanol or 2-butanol and why? What would we call this? Anybody wants to explain?
So would it be 2-butanol because when you're numbering it, you number it in favor of the branch so that it ends up on the lower number?
Wonderful. So if you were numbering that way, we see where it is on carbon number 3, but you need to remember you number in such a way that it ends up on the lowest carbon possible. And so here That makes a difference. So please, this is what we're talking about. You have to apply that because in the realm of these two compounds that we looked at a while ago, where we look at the alkenes and we look at the alcohol, I'm going to discuss isomers with them quickly. Now, isomers are technically compounds having the same molecular formula but different structural formula. So they have the same molecular formula, but when you look at the structure, they are different. And so I'm going to be using this as an example. Now, there are two ways to form isomers: moving the functional group. So one way, and that is easy. Well, let me not say easy, but you can relate to it with the alkenes and the alcohol. So for the alkenes and the alcohol, usually when CXC is testing your knowledge, they really just don't ask you to create any branch. So they normally just say, hey, how can I give me an isomer of an alcohol, or if they provide the structure, they provide the name or whatever they have done, they don't go hard when it comes on to the alkenes and the alcohol in terms of providing the isomer. Usually they ask you to give one that is not branch. So an unbranched isomer where you don't have to branch it off, and later on we're going to be talking about that. So the other one is to form a branch. So with number one, it normally applies to the alcohol and the alkene, because as I said before, they're not going to really give you an isomer question for a acid because the functional group is normally at the end. So people don't move that around. It's always appearing at the end. So we just said that this is 2-butanol. We, if it is that we ask to give an isomer, can we give this as an isomer of that we just did? Is this an isomer? And as you go and you look, tell me why. If you say yes, tell me no. Or tell me why you say no, tell me why you say yes. Can this be an isomer of this? And this is a H, guys. Sorry about that. This is an H. Can this compound be an isomer? So we said that whenever we're creating an isomer for the alcohol or the alkene, we can simply move around the functional group. Is this an isomer of this?
Yes, sir.
Why you say yes?
Because it would have the same like molecular formula because it has the same number of carbons and hydrogens. The only thing that's different is that the OH is in a different spot.
All right. So again, I'm gonna ask you. based on the spot that it is in, would it be different? So Miss Samuel says it's an isomer. Anybody disagree?
Yes, sir.
So why you disagree?
Sir, because if you're naming this compound, you'd start from the right side and it would still end up on the 2. And you still get back the 2-butanol.
I don't think I said that this is your right, you know.
The left.
All right. So point to note, prime example. If I go 1, 2, 3, 4, or 1, 2, 3, 4, the OH is on the third carbon going that way. But if I go this route, it's on the second carbon. And I hope that we're now seeing the importance of why we have to be able to number the carbons so that they get the lowest. Because if you do that, then automatically this again, while this have the OH down the side here, even if it come down this side here, really and truly you have to start numbering so that it gets the lowest number. So technically, this is still 2-butanol. I realize I never spell that. Cool? So this is really a mirror image of that. So where can we actually have a isomer? Can we have an isomer? And if we have an isomer, where would we put that OH? So if we place the OH on the first carbon, so you're in the exam, you can move around whatever functional group, the double bond or the OH. And I think the OH is a little bit more easier than the double bond because through the double bond is between 2 carbons. Sometimes persons tend to have a misconception that it's where the double bond starts. So the OH is just definitely on one single carbon, so it's much easier. So here, if the OH is on this carbon, then automatically this must be carbon number 1. And so this would have been 1-butanol. Now, we said if you want to check it, all of these would have then been the same molecular formula as this. So if I come like this, guys, and I draw the OH, let me erase this. So if I draw this then, is this different from that? Is this an isomer? Would this be an isomer? Look at this. So we just drew 1-butanol. Will this be an isomer? Anybody? Oh, not getting a response. Where them gone?
Sir, is it no? It's not.
Go again.
Cause, sir, like, would it not be because, like, it's still, like, when you count from the other way, it'd still be one butanol?
Wonderful, Miss Samuels. That is it. So again, you couldn't go in the exam and they ask you to draw an isomer and you draw this and say, oh, this is now 4-butanol. So you'll never have a 3-butanol or a 4-butanol because you have to number so that they get they're on the lowest carbon possible. So that is it. So the two would have been either you have 1-butanol or 2-butanol. So same for the double bond. Same concept for the double bond. The double bond is a functional group, and so we just move it around. So if you have this, automatically we have to start numbering from this side. Not true? So this must be my carbon number 1 because we have to try and ensure that the double bond starts on the lowest number carbon possible. So this would have been 1-butene. So if they ask you to draw an isomer, can you draw this and say, oh yes, this is an isomer. This is 4-butene. Sorry, 3-butene. Can we have that?
No, sir.
Because what would have happened is that we now have to start numbering from this side. So again, this would still be considered 1-butene. This is just a mirror image of that. And you know, when a mirror actually flips, so technically what is there is now at the end. So this is a no-no. This is not an isomer. So again, we have to think about moving the double bond. So this is how we get it to become an isomer. So we move the double bond, whichever way you count in this case, you will recognize that you're starting on the second carbon. And so it no matter which direction you count from. So this is going to be 2-butene. So now this is an isomer of that in the way that it's a different structure. When you look at it, they're different. The double bond is in a different location. But if you check the concept of the amount of hydrogen and the amount of carbon, you will get back the same molecular formula. So that's what we mean. Isomers have the same molecular formula, but the structures are different. So we're going to be doing the erasing again. We're looking at compound C. Compound C, Do we see the functional group in compound C? What's a functional group in compound C? What's a functional group in compound C?
Sir, the carbolics group.
Compound C, compound C, compound C. Which one is compound C? What is compound C, guys? Usually persons know those, because if you don't, that's normally where teachers will start if you don't know those. So we are seeing, go ahead, go ahead.
Is it alkenes?
It's an alkane, because we're not seeing any other functional group. We're not seeing any OH. And again, if you would have had an acid, we will see it at the end. We're not seeing any OH. We're not seeing any double bond. So we know we're in the realm of the alkanes. Now, I want to bring a little scenario here. Now, again, how we name the alkanes or how we name any organic compound, we look at the longest chain. So the longest chain have how many carbons?
4.
And we said that when that's our prefix, our suffix is going to be the homologous series. And we use ane. So this must be
Butane.
nice. Now, I want to talk a little bit about how we now form isomers. So we learned how to form isomers with those functional group where we move them around. With the alkane, it's a little bit different where you actually take off a carbon and you let the longest chain become shorter. It's just a technique that we use. So we move around that aspect of that carbon that we actually took off. So in essence, if I'm asked to form isomers of this, the first thing I want you to do is to make the longest chain one carbon shorter. Now, if this is the case, what is the backbone name of this? The backbone name. Backbone name. Since it's going to have 3 carbons.
Propane.
So propane. Wonderful. Now, guys, when you're doing the formation of the isomer of an alkane, the rule is the 2 N carbons cannot accept remember, we have one extra carbon where we're going to try fit at a different location. So if I put the extra carbon here, is this different from this? Let me clarify. When we are in the whole concept of roads, and we have this road, but we have this road. And we have this road. Are these, which of these, A, B, C, which of these are actually different in terms of the concept of roads?
A.
A is different because we see one next road a branch off, not true?
Yeah.
So sometimes we have one straight road like C, But sometimes we have a road that is curving like you're going at the hills up them place there. Give me one of them country place there. Who come from country in here? Country? Give me one of the country name them no? Country road them. Like Fern Gully or one of them place there. Where the road them are go winding. Yeah? Is it that that road is more than one road or it's still one road? It's just that it has curves. Yeah? So if me I travel upon that road, yeah, versus traveling on this road, me still up on one road. But this has a road that is connected to it. So it's the same concept of this. When I tell students, oh, you do say if you have this and you're following the chain, right? This organic compound right here is like one road. So this when you put the carbon on the N carbons here, you're technically just making a bend. And so you're not considering creating an isomer if you place the carbon that you're placing on the 2N carbons. So again, I should not be creating an isomer and I'm putting the carbon on the N carbons. Not true. So I can't put it here because I'm still going to be getting butane. We can't put it here because I'm still going to be getting butane. The only way we can put it that the only other option again is to place it on the carbon that is in the center. And that's right here. Now, watch me now. I may have to use different colors. It doesn't necessarily mean that this is the longest chain only. You can look at that as the longest chain. Somebody else, I may have different colors so I can use it. I could look at this as the longest chain. Seen that? So this right here, somebody else, I could look at this as the longest chain. So please just look at the colors. So the yellow, I think me draw the yellow properly. It looked too like a curve right here. We have the red, we have the purple. Those are different ways we can look at it. Usually though, because we're human beings, we would have been looking at it in this concept, usually. But nothing is wrong with you interpreting it in any other of the other directions that we just ventured in. If I say this is my longest chain, then fine. So usually when we have this situation, it's like we're now saying is this road we create A, where we have that this carbon is not a part of the longest chain. It's like a branch will come off. So the longest chain is wherever you look, however you look at it though, how much carbon is in the longest chain?
Three.
Three.
Right. And so the backbone name comes from the amount of carbon in the longest chain. So what is the backbone name? Propane. Now, here's the thing. For this, it's a little bit easier, or let me say, you don't have a variation, because if I number going this way, so when you now have a branch, The aim of it is just as how you treat your functional group. So you need to ensure that the branch is on the lowest carbon possible. So you number both ways. And again, like I said, with this, you're not going to see no variation because here, what happened? If I number that way, the branch ends up on carbon number 2. If I number that way, the branch still ends up on carbon number 2. So we're good right here saying creating this. Now, we have to tell persons where the branch is. We had to tell persons where the double bond is. We had to tell persons where the OH was. So it's the same concept. But you see, this little thing right here, what we call the branch, this branch has a name. When you have a carbon outside, it is outside of the longest chain, and it has, or a branch that has only one carbon outside of the longest chain, we now call it a methyl group. So we have to tell persons that there's a methyl group present in this compound. So I can't just leave this and say propane and don't tell them, because again, for isomers, they should have the same molecular formula. Which brings me to another important point. Not because this isn't a part of the longest chain doesn't mean that you don't take it into consideration when you're doing your calculation of how much carbon there is. So a popular mistake that students will do is to call this C3. We cannot call this C3 because it still has in 4 carbons. It's just that the structure is different. So it is still C4. Cool? So while we take out one of the carbons to move it around to form the isomer by creating that branch, when we're devising or creating that molecular formula, we still have to include this carbon in the molecular formula because it makes sense. Because we should have the same molecular formula for the two of them. So this is the isomer of that. So let's talk about where. Please remember the number is a representation of where, which carbon the group on, which carbon the functional or the branch is on. So we have to tell persons, hey, on the second carbon, there is a methyl. So we say 2-methyl, again, we separate that number with a dash because it's meeting a letter. So we get 2-methyl propane. 2-methyl propane still has, and you can count it up. Again, I did not put in all my hydrogens. No one to kill me. But we should know that they're there. We should draw them. I may be doing that due to the interest of time, if we draw back all of the hydrogens, and my focus point is not really the hydrogens now, is the branching and the naming. So again, when you're in your exam, do it in its entirety. Put in every single, once it's the structural formula, place every single hydrogen and branch, double bond, functional group, wherever. Okay? Yeah? Do we have any questions so far? Anything? hear no from one person. Everybody else is good?
Yes, sir.
All right.
Yes,
So
sir.
so we would have had the 2-methyl propane, and we said this is an isomer. Stressing it again, isomers have the same molecular formula but different structure. So this look different from this. And so CXC sometimes even the multiple choice, them love do it. So they will show you this, and I'm just drawing, and then them show you this. Is this different from this? Is this, so this is A and this is B. Is this different?
No, sir.
So they're popular, and they will give you this as C. Let's put this as a C, and then they give you D. Them could have give you something looking like this. And I said, you know, which is the isomer of butane? That one. So don't think, and this is the other thing that assist students don't really understand as well. You see, multiple choice can also be practice for your paper too. You see, paper two can also be practice for your multiple choice. And so don't just try to, and I hope no student is inside this group and no person's bank on the fact that multiple choice repeat, multiple choice repeat. So even when they're practicing, they just go and say, oh, if me see that question here, that would have been the answer. Sometimes it's the truth, and in fact, the multiple choice do repeat. That's a fact. You're going to see some of the multiple choice. But God forbid the option changes. So students even go as to try and say, oh, say the answer A. If they even move the same answer, go down at D for the next question, I see students getting it incorrect because they try to study multiple choice questions. You should know. So be able to reason out why such and such is the answer. All right. Now we jump into D. D, 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 D. What is the homologous series of D? Anybody? When we look at D, what's the homologous series? So we're seeing D where we have this, yeah? So go ahead. I don't know if it's for me only, but you break up, not hearing you clearly.
Sir, is it the
One second. Yes. All right. So we know it's the carboxylic acid, and we know it based on this functional group. Now, I've seen students say and ask me the question, but here's a double bond. Why don't we call it an alkene? And just to clarify, the double bond has to be between two carbons. This double bond is between the carbon and an oxygen. So that's one. The other thing that I'm talking about, this area is a functional group. This is a target of all reactions. This is where reactions will take place. Next thing, we said that, technically, once you get a carboxylic acid or an alkanoic acid or an organic acid, the functional group is always at the end. So you're not going to get a lot of, well, you won't be getting any isomer question along this line because you're always drawing this part at the end. So what is the name of this? We end by saying anoic acid. So the prefix based on the amount of carbons, and then we say anoic acid. So how many carbons are there?
3.
So what's the prefix for 3?
Pro.
So this would be called propanoic acid. And that's how it is for all the acids. So all you do is to, just like any organic compound, you have your prefix and you end with anoic acid. Now, I want to do two things. I want to go back to when you were doing the common acids, the common cations and the common anions. And I even going back to the acids. Organic acids they basically are made up of two parts. So let's go back. Help me out. What's the name of this acid? What's the name of this acid? What them there?
Hydrochloric acid.
Hydrochloric acid. What are the name of the acid here? So if this is a hydrochloric acid, what are the name of that one here?
Whatever hydro, bromine acid.
Hydrobromic acid. So what are the name of the acid here?
Sulfuric acid.
Go again. What's the name of this?
Sulfuric.
Alright. So what are the name of this one? What them there? When I start read over back acids and base yet. Phosphoric acid. What the name of this one here?
Nitric acid.
Alright. And so if we examine all of these acids, all of them, the thing, what is it? And I know you need to remember this is going to where the cross comes in with organic and going back to acids and base. So you can get an acid and base question going down into the organic section because a part of organic is the organic acid. Each acid provides what we call hydrogens, the hydrogen ion. That's what makes an acid. Remember about dibasic, tribasic, monobasic acids as well. But for this particular acid where we have here, so this acid Look where the hydrogen is. Now, the hydrogen in question is at the end persons because remember I told you, you see this little part is really this. So when you write in the molecular formula, or this is technically the condensed structural formula, when we write, and I soon talk a little bit about the molecular formula, when you write in the molecular formula, we are used to, look at these, we are used to putting the cation first. So the acid is made up of a cation and it has an anion. And so the cation comes first and the anion comes after. But for the organic acid, the organic portion gets preference. So if I break this up into the two ions, I'll get H plus and Cl minus. For this ion, we got the propanoate ion, which is that, and you have the H plus. Yeah? Why am I going through all of this? Because if normally they come and even though I never mention any form of reaction for the other organic compounds, I want to highlight this because in case students sometimes fall down because they don't remember that technically the hydrogen is going to be replaced. We need to remember the connection between the acids and the base knowledge that we learned. So if this react with a metal, don't forget that when acids react with a metal, what is formed? When acid react with a metal, what is formed? Acid plus metal. Acid plus metal. With them there. Acid plus a metal. We have to start read over, guys. Have to start read over. Acid plus
Salt and hydrogen.
salt and hydrogen. Yes. Yeah. Because technically, what you find is a single displacement reaction where the hydrogen is going to be kicked off. Now, why I'm mentioning this as well, students will ask me sometime, but sir, there are other hydrogens in this compound. No, they're not going to be the focus point. It's the hydrogen at the end of the acid. So technically, when we're writing the formula, this is how we write it. Yeah. Now, what is the general formula for an acid? Somebody tell me the general formula for an acid. General formula for an acid.
Could have 9 hydrogen and COOH.
Thank you so much. So again, is there anybody in the group that don't understand how we would have gotten to this?
Same.
And let me take it a little bit further. We can we can have this. We can have this. We can't have that. This is a representation of this, not true? So technically, the molecular formula tells you how much of each atom. So CXC can give you this. You should know automatically. Why would you know it is not an alcohol but an acid? The fact that we have two oxygen. So the moment you see two oxygen, you know that you're dealing with the acid. If it was an alcohol, then you would have had one oxygen. Maybe the numbers, you understand? So the fact that you're seeing two oxygen, so bear in mind, this can be presented to you. So you should know. You should be able to deduce which acid this is. Because the moment you see this two, you must know say I want acid. Because only acids would have had the two oxygen. If it was an alcohol, it would have been one oxygen. So again, we want to take it, just run through it just in case, because of the concept of how we illustrate the acids. When we say CN2N plus 1, for N we use one less carbon in the formula. So if the carbon compound had two carbons, for N we use one. If the carbon compound, like pentanoic acid that we just did, you had 5 carbons, we use 4. And that is critical when applying the general formula because it will mess with the amount of hydrogens you have. Now, as well, do remember that these acids, when it comes on to them reacting, it's going to be that hydrogen at the end that is being replaced. You should also remember that it follows the same concept of your previous acids that we have. So just like our metal will react with hydrochloric acid, giving you the salt and water, it's the same way these acids will provide you with salt and hydrogen gas. If they're reacting with the base, it is the salt and water. If they react with a metal carbonate, is the salt, carbon dioxide, and water. It follows the same principle as these acids in terms of the reaction. The only difference is that the hydrogen is written at the end. Now I want to mention as well the naming of those salts. Now usually I have magnesium reacting with hydrochloric acid. What's the name of the salt that I will get? What's the name of the salt? What is the name of the salt?
I can do it.
Repeat the question, please.
I have magnesium metal reacting with hydrochloric acid. What is the name of the salt?
Magnesium chloride.
So we're going to be forming magnesium chloride. And we said that this is a form of single displacement reaction where the magnesium is more reactive than the hydrogen, so it gets displaced, and hydrogen is a diatomic atom, so we form that. right? And remember, you're going to have to put in your state symbols and all of that. The point of me doing this is not to focus on the balancing or the acids and base right here. Let's replace this with something like the same propanoic acid. Now, what is the name of the salt? Follows the same principle in terms of the name, but it changes in terms of how we write it. I think I should erase this and do it properly. So let's go. So we would have had the magnesium, it's really a solid, plus propanoic acid. All acids are aqueous. What will this give me?
Sir, is it magnesium propane?
Did you say magnesium propane?
Yes.
No, not propane.
Propanate, NATE is supposed to be on it now.
Yes, so propanoate.
That.
So the thing is, here's where some persons go incorrect. We don't put the magnesium at the front. So this is a very important reaction. So now, this technically, which hydrogen was replaced? This hydrogen was replaced. And so, because this is a polyatomic ion, magnesium ends up at the end plus the hydrogen gas. Now, even though the magnesium, so this is the scenario, so they can react it with calcium, they can say it reacts with sodium. Please remember that the anion in the acid comes before the metal in this case. So we end up with the propanoate ion, but when we're saying the name, we say the metal first. So we're going to call this magnesium So this is the salt, magnesium propanoate. If it was ethanoic acid, it would have been magnesium ethanoate. If the metal change, say if it's calcium and methanoic acid, calcium methanoate. So all you need to remember is that what will happen, and it follows the same principle of you writing your ionic equations. So this is actually the anion. So it is a negative. So remember the magnesium would have been a 2 plus. And so when we basically write the magnitude of this, we end up have to put this into bracket and put the 2, right? And so with this, even for this, we need to balance because this is 2. So we'd have to balance by placing a 2 here, right? And that's how we would have had a balance equation. So all of this, the real focus, I want you to pay keen close attention to. So this is even one of the reactions of the acids. Acids, the organic acids can react with metals. When they do that, the hydrogen in the functional group gets replaced by the metal. It is written at the end, but when you're doing the name, the metal comes in front. Cool?
So,
So the question A would have said, name the homologous series to which B belongs and give a reason for your answer. Which homologous series does B belong? And B would have been this, guys. So which homologous series does B belong? I'm not sure if you open your mic and said something and then,
sir, will it be alcohol?
and they say why.
Because it has an oxygen and a hydrogen connected by a single bond.
All right. And I see what you're doing right there. So wonderful. But what we call it the hydroxyl group. Because I know you want to make the distinction because you couldn't just leave it as at that oxygen and hydrogen because the acids too have oxygen and hydrogen. So the name for this though is an hydroxyl group. So we're seeing the hydroxyl functional group, so we know that it's an alcohol. Beautiful. It says define the term structural isomerism. What is structural isomerism?
Where have different structural formulas and the same molecular formulas.
Wonderful. So when organic, and one of the reasons why I'm repeating, I'm not sure if persons would have been hearing because I kind of hear a little breaking up. So it is the creation where you have compounds having the same molecular formula but different structural formula. They would have said, draw the fully displayed structural formula of one isomer of A and name the isomer. So isomer of A, remember A would have been the butene. So they would have asked you for an isomer of A. So technically they want an isomer of this. And we said that when we have the double bond, right? Because you can form a branch, right? But one of the easy isomers that you can determine is to create that situation where you place the functional group in a new location. It says describe one chemical test that could be used in a laboratory to distinguish between A and C. Now A is an alkene. C is an alkane. Now popular question by CXC. They love to ask it. They love to ask it. But even though I say popular, it doesn't mean that it might come. But in case it comes, what we do is to utilize bromine water or acidified potassium permanganate. Now, the thing about it, the alkanes, in order for them to react, especially with the bromine water, they need ultraviolet light, UV light. So what you can say in the laboratory, if you react this without UV light, then no reaction will occur. Bromine water is reddish brown, and so the water will remain reddish brown. No reaction will occur. So for ease, we just say that we can react either of these substances with bromine water or acidified potassium permanganate. In the case of acidified potassium permanganate, again, if you put the alkane, you're not going to have a reaction, and so it's going to remain purple. Now, that is due to the fact that alkanes are saturated. Alkanes are saturated. Now, alkenes, on the other hand, will react with the bromine water. They will react with the acidified potassium permanganate. So it will decolorize the bromine water and it will form the colorless alkane, right, with the branches represented on the various carbons where the double bond was. And maybe that's another thing when we can look at some of the reactions. We also can react potassium permanganate acidified with the alkene. A matter of fact, we use that to form the diol. When we're reacting the water and the oxidizing agent, we get the diol. And again, you can look up that reaction. So alkenes will react with bromine water and acidified potassium permanganate by decolorizing both, while the alkane will not. And so that is a prime example of how you distinguish. But I want to end by also saying, because of how they burn, you use that as a means of distinguishing them as well. Alkenes burn with a yellow, sooty flame. So when you burn them, you ever see that black, like when you light a lamp, you see that black soot fogging up the lamp, and once you finish with the lamp, you have to clean the lamp shade. I don't know how old some of you students are, or if your parents still have those lamps. We improving technology. We have those little flashlights, we have rechargeable lights and all of that, solar lights. So persons, for one or two reasons, because of the safety, lamp can get blown over, especially like in these windy time. So we kind of limit that, but that's how they burn. Now, the alkanes, they burn with a blue flame. And so if you hear from one of those gas commercials, one of the things that they will promote as as the gas to purchase is because it burns with a blue flame. It makes it much more healthier because less carbon is given off. So one of the reasons why you're getting that sooty flame with the alkene is because of we don't call that now, the ratio of hydrogen and carbons. So the carbon is not being burnt properly. So you get that black, yellow flame. While with the alkane, you get the blue flame. And that's why we said that they promote their propane and their butane in their liquefied gases. So this brings us to the end of this session. I do hope it was beneficial. Again, even with this being an extra class for some persons, or for most persons, what you will do is never enough. Always continue to do some work on your own. Capitalize on the time. It's drawing near to your paper 2, paper 3 exams. So get the practice in. So again, we finished another session, and I hope you can use this to prepare for your exam.